everybody. Thanks for having me. This is my first time, and I was supposed to go second, so I was hoping to get a beer before I would start this, but no, life is hard. No beer for me. Hopefully afterwards. All right, thank you so much. So thanks for the introduction. So I don't know how much you actually heard, but I am at the Florida Space Institute, and I feel not enough people know who we are, so look us up. We're currently under UCF, but we do a lot of astronomy, experimentation, we build CubeSats. So, you know, like I see there's younger people in the audience, as well as, you know, everybody. Feel free to look us up, and we have extraordinary training opportunities. Louder? I feel like somebody's saying louder over there. I don't know. All right, so my mom, she didn't really think I should do a PhD. She was like, no, that's for, you know, I don't know, people who don't know what to do, you know, like it's for people who don't look like you. I was like, yeah, I'm going to do a PhD. So then later, wait until she heard what this was about. It was about dust. So she was like, what? You have plenty of dust in the house. You don't have to do a PhD for that, but it turns out dust is very interesting. And actually in an even biblical way, right? We're all made of dust and we'll all return to dust. So this is actually literally true. So is that fine with the sound, or I don't know? Here, you good? What? Closer? Oh my God, yeah. Okay, I'm just gonna imagine this is my beer. Okay. So our dust, you know, when you hear about the solar system, you think, oh yeah, the sun, the planets, but there's actually a lot more in there. There's a lot of loose stuff, and it actually all started as loose dust. So, and this dust that remains in the solar system, right, it retains history, it retains information of what was going on before we had the planets and how the planets were formed. And so what I'm looking into a little bit is, you know, like if we look at this dust and we look what it does and how it behaves, what are the secrets we can unveil? Let's see. And so I started my science career working on planet formation. And planet formation actually happens in very beautiful looking clouds of dust and gas. And in these clouds, new stars are formed. So this is the Orion Nebula, and those are Hubble pictures of new systems, new stellar systems, I guess, that are formed. And around each of those new formed stars, you see there's like a remaining disk of gas and dust. And you know, right now it's actually a really exciting time to be in that field because, and I will tell you why, we're getting a lot more information than we used to. And starting with the Hubble pictures in the 90s, those were the first kind of pictures where our idea of how planetary systems were forming and planets were forming from dust was actually could be observed, right? We would see these young stars and we would be like, oh yeah, this really looks like places where planets are forming. And so why is it so interesting to be in planet formation? Well, for a whole while there in the history of humankind, we thought there's 9 planets, 8, you know, for some of us. There's our system, and you know, there's life on our planet, and that's pretty unique, right? So the life part is still pretty unique, we're still searching, but turns out that the planet part is not unique at all. Turns out that there's, you know, a lot of planets out there, and this is actually, you know, something we've started to learn just in the last couple of decades. And there is now a website where you can just go and pull this plot. And so when I prepared this presentation, maybe February of this year or something, I just went on there and I asked, please show me all the planets that are out there, you know, with how far they are from their central star down here and how big they are up here. And this is what comes out. These are hundreds and hundreds of planets. So something's going on. Planets are obviously forming very easily. This is not something special at all. Our solar system system in that sense is just one, of many. Then we have other new facilities that allow us to really look at these planet formation environments. So these were the Hubble pictures from the 90s, some of which I showed you earlier in the Orion Nebula. And now we can look at a disk like that with this kind of resolution here, where you will even see the gaps that are opening, the structures in the disk, and basically you're looking at a system that is currently forming planets. And this is possible because of large arrays of telescopes that are in, high up dry places. So that's not Florida. It's more like Chile. And they're now doing, through interferometry, in the millimeter wavelengths, they're able to actually see. So the colors here are basically millimeter-sized grains, millimeter to centimeter-sized grains. So, we gone from this, okay, it must be dust, to, we see exactly where the grains are and the structures in the rings. And that is also rather recent. And then we've recently also had several actual space missions that went to study asteroids and comets, which are basically loose collections of dust, which has been shown by these missions. So here, that's the Japanese mission, and you can see this is a very cool picture. This is the shadow of the spacecraft overflying the asteroid Ryugu. And they touched it and they collected samples and brought them back, and so did the US with the OSIRIS-REx mission. And we also had a very awesome European mission to the comet 67P. I'm not going to say the name. It's a Russian sounding name, sorry. But all these missions have shown these are not just pieces of rocks that are flying through the solar system. These are a collection of dust and rubble, the so-called rubble piles. And so these missions, so we've now gone to these places to see that there is dust, basically, a lot of dust out there. And then finally, last but not least, there's also a lot of laboratory work going on to understand how the dust behaves, how it would be possible to aggregate it at smaller sizes, how it would be possible to grow a body. So for all these reasons that I just told you, being in, the dust business is very interesting these days. We're advancing a lot our understanding of what's going on in the planet formation business. And so really planet formation starts with very fine dust, micrometer sized. So I don't know, how thick is a hair? Anybody knows? It's like thinner than a hair, right? So a micron is, and so all these dust particles, and that one is an artist view, although we almost get these type of images from the telescopes now, but that one is an artist view. And the dust in there, it's about, it's very fine, tiny grains. And that's how it all starts. And in the end, we have planets, right? So the planets can be very big. Some of those Saturns and Jupiters, they're huge. So how do we get from this very fine dust to these huge planets? And, that's what we do, the physicists, right? We usually assume the horse is a sphere. I don't know if you heard that joke ever. But we make assumptions so we can keep progressing. And the usual assumption was, it just aggregates, so here you have, your two scientists, they're having their equations of the star, that's our dust here, and those are our planets. And then in the middle it says, then a miracle occurs. And that's how we were operating for a while there in planet formation. This dust, it must be sticking together, and then it just grows into planets. And then the teacher says, I think you should be more explicit here in step number 2. Well, so that's what we're working on, basically. So there's classical models. So how do planets form? So you have your new star forming, and through conservation of angular momentum, basically, if it turns, it's going to keep turning, and if it gets small, it's going to turn faster. You start having, first it's a cloud of gas and dust, and then you start having a disk. It settles down to a disk. And, the first thought, the simplest model would be, well, it just settles in a disk, and wherever you have dust, you're going to have these planets aggregating. The dust is going to stick to each other, and then going to form planets. So that means that you would have, just more material up here, because you had, as you would leave out, you would have less and less material. So you would have more material here to make planets, the terrestrial planets, and then less material, but then all of a sudden, this is the snow line. So here, ice cannot exist, it's too hot, but ice starts existing here. So now you get all the icy material. So there you're going to make large planets, because there's a lot of extra material through these ices, and then again you're going to make smaller planets as you go out because there's less material. So you can kind of explain, okay, Venus, Earth, Jupiter, Saturn, Uranus, Neptune, by saying they're formed where they were in the disk. But this is a distribution of mass in the solar system. This is Mercury, and this is Mars in the asteroid belt, and these are the giant planets here. So you can explain 1, 2, 3, 4, 5, 6, out of 9 things we're looking at mass-wise, and good enough. That's 2/3. But what's going on with Mars? What's going on with Mars and with the asteroids? What's going on with Mercury? And that's how we kind of started, looking more into it. But basically, classical models, as I just said, they would say, okay, Jupiter and Saturn, they were made where the ice was present, so they were giant planets. There was a lot of material to make them. They were able to aggregate all this gas. And then Uranus and Neptune, they were smaller. They still had more material because of the ices, but they were more out there at the outskirts. But the problem now, there's several problems. With all this new data we're getting, what are we looking at? We're looking at these disks themselves, and we see there's certainly not a smooth distribution of material from the center to outside. If you remember a couple of slides back, and I'm not going to bore you with equations, but this here basically says there's a smooth distribution of material. There's more here and less out here, and this is the law by which it decreases. And now we're looking at this structure, and certainly it doesn't just have more material here than smoothly go down there. So overall, yes, but there's places where there's much less material than there, and those are more inwards. There's places where there's less material here for some reason. So the fact that you just have a smooth distribution of material isn't really what we see. We also have now new information from experiments. We started checking, okay, you're saying these dust grains are going to just grow and aggregate and form larger dust grains. Let's look at it when they're so small. We can actually try that. And turns out that works well when, let me see, there's kind of a video there. Can I just try to click that? Oh, it's sad. No videos? Anyways, this shows you that dust grains, an actual experiment where you see dust grains growing. So they're very small, it's working, so we're like, that's good. But then, it turns out when they start growing just a little bit more, the millimeter range, so let's see, like this, like a bead, a pearl you would have on your necklace, it doesn't work anymore. So none of my videos are going to be working. I'm just trying this real quick, okay? No? Okay. Is this PowerPoint? Is this PowerPoint? Is this PowerPoint? Okay. All right, anyways, let's talk about this graph. Well, maybe if it were working, it would be awesome. Well, these two, just spoiler, that's maybe a small golf ball size dust aggregate. and it gets dropped onto another one, and they just crash in 1,000 pieces. And that's just a golf ball size, dust aggregate. So how are we going to make planets, So what's happening here, this is time down here in years, and this is the size of the average grain in the disk. And so, when they're small, they grow, it's working like we thought it would, but then they reach, the bead/golf ball size, and something happens. They no longer grow. They stagnate in size, and then they just don't grow. They keep hitting each other and eroding each other, and the whole disk is not experiencing a population of grains that is growing. This is called the bouncing barrier. It turns out that if you start looking at whether dust sticks to each other or not, it's not working beyond, the golf ball size. So problem because we see planets, so something's going on. And so, and then the last thing, it seems also that there's a lot of material that was mixed. So remember, a classical model says what was in the inner solar system made a planet there and stayed there, and what was in the outer solar system made planets out there and stayed there. But it turns out that if you look at all these exoplanets, all these planets around other stars, you see huge Jupiter-sized planets that are closer to their star than Mercury is to the sun. They're like orbiting in just a matter of days, spinning like crazy. And these Jupiter-sized planets must have formed when there was a lot of material out there beyond the snow line. Yet we see them inside, very close to their star. So they must have moved there, So something's moving. And then this chart, that is study made on meteorites. So meteorites are stones that fall from the sky onto, our labs, into our labs, and then on the ground, I guess, and we pick them up and then we study them. And those meteorites, they indicate, this specific type of meteorite, indicate that there's two types of meteorites. And you could only get that if you had two reservoirs of material that produce these meteorites. One type of meteorite, these materials were inner solar system materials, like Earth and Mars meteorites, they kind of have these characteristics. But then there's a second type of meteorites, and these must have formed in the outer solar system. So you have two reservoirs, okay, so far so good, because we said inner, outer, nothing's moving. But then we get this type of meteorite here, where it's all mixed up. All these two reservoirs came together to make this meteorite. And so here's what must have happened to make that possible. You had, a planet forming, like Jupiter, creating two reservoirs. But then Jupiter started moving around. And by moving around, it threw material from out here inwards and material from inside outwards. And that's how we ended up with a space rock that has a mixture of these two reservoirs. So obviously, stuff doesn't just stay in place, it moves around. And so, there's lots of avenues to basically advance our understanding of planet formation. We can look at, these systems that we talked about. We can do some modeling, laboratory research, and in situ investigations. And the thing I am working on is a little bit more on the laboratory side of things. And so I study this dust, like how did this dust come together to form planets? How did it overcome this barrier of growth I talked about? How did it mix in the solar system? And so real quick, I'll just say, also when I say dust, I'm very open-minded about it. It doesn't have to be the size of, the dust you would have in your house, like my mom thinks. It can be like sand-sized, but it can also be boulder-sized. It can be, like gravel or boulder. This is all considered dust. It's basically all that is not a giant space rock the size of this room. So, if you see meter-sized boulders, I don't know, like size of this barrel, that's still considered dust, And then regolith, ever heard of that term? Yes, regolith is the dust that is on the surfaces of bodies and planets. So it's also dust, it's just collected on the surface of larger bodies. And some of these just shed dust, like this is an asteroid that's just losing dust. And then sometimes you can see also, in our solar system we have a cloud of dust. It's called the zodiacal cloud. Yeah, nobody knows. Tomato. Potato. So anyways, there is a kind of a dust ring in the solar system that you can see in certain, sunset conditions, like here, for example. So, there's dust going on, and I'm not very picky about the size, is all I'm saying on this slide. So here on the moon, for example, that's called regolith, but you see, you have like a boulder like that, and then the finer dust, for me, would all be called dust. And then, this is an actor's picture of protoplanetary disk. So then, you can have different compositions as well. I'm not set on it has to be mineral dust. It can be icy dust. And that video, for some reason, is working, which is great. I guess I would only use GIFs in the future. This is an actual recording of what's going on the comet 67P that was visited by the European mission Rosetta. And you see it's very impressive. This is towards the neck here. And it has these cliffs, it's like kind of a bilobate body, and it has a neck. But what I'm looking at is all this dust that is flying around, most of which are ices, because the comet has a lot of ice grain activity, because when it gets closer to the sun, it gets expelled. So, I'm not too set on what the dust is made of. It can be minerals, ices, it can also be organics. And so organics, that's like, what we're also looking for technically to see how, proteins could have formed in the solar system, and then eventually us, down the line. But, so, the dust can be made of several things. And so, let's see. So here I just put a few ways that we use to study the dust. And there's, you can look at the sky, at the interstellar dust, planetary disk. You can go with the missions and do, fly by some of these dusty bodies, do some remote sensing. You can collect interplanetary grains. That's also very interesting. You collect them. Some of them made their way back to Earth. That was a mission a while back. I don't remember what it was called, but they had captured, dust from the solar system by just flying through this empty space into aerogel, and they brought those samples back to Earth. And then you can do landed surface studies. So this is all very exciting, but not everybody can participate in those. But laboratory work, again, where I'm at, you can do dust behavior observations and also composition analysis. So I actually work on both, but I'll talk just a little bit about dust behavior. And of course, it's kind of disappointing if none of these videos are going to be working. But my golf balls here, they very gently touch each other and then bounce off. So there's conditions under which you get some bouncing, which compacts them. So now they're stronger, and they're still not forming any planets. And then this guy here just crashes on this other guy. That one's like a marble, and then completely explodes. So those are the kind of experiments that I'm doing. And okay, well, it doesn't work, but you can see the concept. Initially, you had two of those balls made of these grains, and the top one just completely engulfs the first one. So we're trying to see if under certain conditions, you could still grow by, for example, accumulating mass from a fragmented body, for example. But really, what we're seeing is like it's not advancing very much if we just try to grow by aggregation. And so that's another study we did. That's an experiment that went to the International Space Station. So we just put our little grains in trays and we were shaking them, and then we were studying how they actually aggregate or not, and whether they dissipate energy or not by all these collisions that they're making. Still more videos. So we are also studying, you can also study how, let's say you made it to a certain size, so now you're a dust kind of layer. What happens if you impact something now, to your dust? Because these bodies have very low gravity, so it doesn't behave like on Earth where it just falls into, the beads and you never see it again. Instead, you get like all the beads lifting up and you're doing a huge ejecta plume. Same here. So we do these studies, those are impact studies, how to poke a loose aggregate of dust that is flying out there and what happens to the dust. Let's see. And so some of these experiments have to be done in microgravity. So who's heard of that? Yeah, not bad. Okay. Where do we have to go to get good microgravity? Yeah, very good. That's a good one. Because one time they served me, Julie went to Finland to launch her rocket because up there it has extra good quality microgravity. So that's not how it works. You can get your microgravity wherever as long as it's falling. So like, let's say you're in an elevator and you're out of luck that day, and the cable that's holding your elevator is breaking, and then you're falling with your elevator around you. Within the elevator, you will experience microgravity. So hopefully you have good foam at the bottom, but there's several ways you can do it. So the falling way is the very most simple one. You have this giant drop tower, that one is in Germany, and you just put your experiment in a capsule up there and you drop it. And for that time that it's falling, you're in microgravity. And so you can also fly free fall parabolas with an airplane. And then you can go International Space Station, good job, it's even on the slide. Or you can just shoot a rocket up and just let it fall back on the ground, and then you get 3 minutes there of microgravity. So why I need microgravity though is because the dust I'm looking at, it has no gravitational pull. So if I want to study how it behaves, I can't do it on the ground. Because if I shoot two things very slowly at each other, they're just going to fall to the ground. If I want to, do gentle collisions, for example, gravity just covers all these forces that are involved, and I can't even do my collisions. I have to go to microgravity to observe these effects of how the dust behaves. Let's see. Or how the dust behaves in its, acceleration environments that it would be in space. And so the dropping concept is also what we use in my lab here. We have two of my students working on our laboratory drop tower, and the concept there is, and you saw earlier, we had, two of these aggregates that were hitting each other. So the concept there is you free fall, a couple of dust aggregates, and during the time they're falling from here to down there, they're in microgravity. And that's enough sometimes. So it's very short, it's under a second, but you can do one collision. And the thing is, because it's your lab, you can do 3 every day. If you have to go to the International Space Station, it takes 10 years to prepare one payload, and then you better pray your rocket doesn't explode or something. That happens, right? Like you prepare your experiment for decades and then poof. So anyway, so less microgravity time, but more accessible. And so what we're looking at specifically is how we collide, we shoot them at each other, but very gently. And so we're trying to see how far can we get with our sticking that we were looking at earlier. And so here's a plot down there is how fast we shoot them at each other, and that's how big they are. And so if they're small and slow, yeah, they're sticking. But if they start growing, and in the disk, they will also start getting faster when they're bigger, you know, you get into the bouncing zone, and then eventually, if you're too fast, you just destroy them. So this is the plot, basically the summary plot of what we're finding in experimentation. So you cannot build planets by just shooting 2 dust grains at each other. Instead, ooh, another video that's not working. Instead, now, you know, our theory now is like there's some effects with the gas. So, I don't know, who knows what a peloton is? Not the thing where you have a trainer that, an actual peloton, the Tour de France, no? You say that, Tour de France, right? Yeah, it's a group of bikers, right? And so, you know, I don't know if you follow, you know, cycling. Like, it had more popular days when, you know, we thought they were not doping, but so anyway, so, you know, you'll have your guy in front of the peloton. He's the one who's bringing in all the work because he's the one with all the air that he has to fight. And all the guys that are in the front row, they're fighting, they're pedaling, and these guys actually, because it's teamwork, they're preparing the road for the guys that are right behind them that are going to go sprinting at the end because they still have energy. In the peloton, you have like the protective layer of the first row of cyclists, and the ones that are in the middle of the peloton, they almost have to produce no effort. And if you had, as peloton, that would have like, let's say, bad wind coming against them, and a lot of guys coming in, they would start accumulating in the peloton because you cannot go faster than these first guys in the front. And turns out that if you start looking at what the dust does when there's gas in the disk, it's kind of similar. You start having, and you know, it doesn't show here, but you start having accumulations of dust in certain places just because the gas is there. It stops some of the dust that is in front. You get all the dust coming in the back, and the front guys are producing all the work. And so you start having concentration of dust grains, maybe golf ball size. And as we saw, they don't really aggregate, but they do collide and dissipate energy. And so they start hanging out, and after a while, there's that many that, poof, you got an asteroid-sized body. So you don't have to stick golf ball size dust grains to get an asteroid. It just comes together because of interactions with the gas, as we would in a peloton. Back to my cycling. I know, I had a dad, he was watching cycling anyway. So, you know, you could be jumping several orders of magnitude in size because of these interactions. And you know, this is where experimentation that we produced is useful. We said, whatever you think it is not, because it's not working. So then other groups of people who do these simulations, they were like, wait a minute, you know, if we do it properly with this information, look what happens. And now we're getting a better idea of what actually happens. It's not just growth by collisions. It's growth by collisions until you're golf ball size, and then it's growth by, you know, gas effects, basically peloton effects. And so you end up understanding better also some of these structures that we see. Because we went to the comet, we went to the asteroids, and we did some radar tomography through them, and we saw they're very loose aggregations they're very porous. Why are they so porous? Well, this formation process that I just described could explain why they're so porous. They're just never actually just hit each other to compact like that. They ended up just aggregating loosely, and at some point they became, you know, enough that they developed their own gravity as a group and started staying together. So then, like, I'm just taking you through some dust effects, you know, because it's supposed to be entertaining. But there's also some interesting effects if we look at layers of dust on small bodies. So these small bodies, they have very low gravity. You know, it's like we would consider that to be no gravity. The International Space Station has more gravity, you know, because it vibrates and has these residual accelerations than these bodies. And so the dust starts doing very interesting things there. For example, that's a moon of Saturn, I think. And you see that's the actual moon here, and it has a skirt. The dust just accumulated as a skirt around the equatorial region. And so these are interesting effects that what would happen if you were to poke this, like not, really go there and poke it, but let's say some micrometeorites, there's plenty of those in the solar system, would come and impact this. Would you immediately lose the entire, skirt of material? Anyway, so interesting features. This is the comet in question, 67P. It has these patches, and you see the neck is where I showed you the video earlier. It's here. So that was also very interesting. This looks like it was splattered, like material just splattered layers on there. And then looking at what these dust layers do, we can also maybe understand better what's going on with these activities. So that's the comet again. And really what you see here, because everybody thinks, oh, we're seeing water vapor because it's sublimating, but no, what you see is dust. When you see it, it's because there's dust. And they were actually trying to relate it to water vapor signatures, and they couldn't always. So there's some dust ejection events that are happening that are not necessarily linked directly to water sublimation. So very interesting features. And that's an asteroid. So this is a comet, okay, fine. We're used to them having tails and activity going on. But that one's an asteroid. So there's a couple of bodies that are like interesting. They're called active asteroids or asteroid belt comets. So they're basically asteroid materials. So they're made of asteroids, but they shed dust like a comet would do. So, these dust experiments that I work on, we can start thinking about why that is happening. And it's probably because the dust just has structural failure. It's such low gravity. These are fast rotators. They're probably just shedding material. And then, understanding how the dust works is also very interesting because we want to go explore and potentially mine asteroids someday, And there was a time where it was more popular to mine asteroids. That was during the Obama administration. Then, then it was the moon, and it looks like we're going back to Mars now. But in any case, if you one day, because there was a mission one time, I'm not sure if you heard about that one, they were going to go to an asteroid and bag it and bring it back to Earth. So could you even do that? That's the question. Like, could you even bring a mining station and start mining this asteroid like they're showing here? Or when you would like approach and touch it, it would just disappear into 1,000 dust grains. So anyway, studying dust in low gravity environments has many interesting things that we do. That's it. I can get my beer. Well, I hope it was entertaining, and I hope it could interest you in dust a little bit. And you get to do that also, that's fun. All right, so do I take questions?
Yeah.
Yeah, sure.
Okay, so does anyone have questions for Dr. Brissett?
So there's a lot of theories out there on attraction or aggregation you're talking about. And we try to unify those with a multidimensional or string theory type of unification. It doesn't seem to cover why these particles aggregate.
So I mean, it's actually fairly simple.
There's some challenges on gravitational theory recently.
Yes.
Whether it's electromagnetic or actually gravity.
So we're not into gravitational theory. We're more into, let's get rid of gravity so we can see effects that are hidden here on Earth because Earth has gravity. So if you were in space and these particles were starting to aggregate, some phenomena are going on there that you cannot observe here. That's why we try to get rid of the gravity. But we're not into the business of the gravitational theory and the bigger picture of how the universe functions. However, I can answer one portion of your question. When they're very small grains, they aggregate through, van der Waals forces. They're like, these atoms that these grains are made of, the minerals, they have some polarization to it. The electrons are not all uniformly distributed everywhere. They tend to have, some polarization, and then when they have two grains meeting, they have a so-called surface energy that allows them to stick. So, they meet, and then, there's some sort of spring kind of constant happening, and then they just kind of stick to each other because these molecules and these atoms, they're just kind of locally polarized. So it's overall neutral, but there is surface effects that allow them to stick. But it only works when they're very small. As soon as they're too big, the masses and the inertias involved are too strong of a force, and it kind of doesn't work that well anymore, the van der Waals forces. So they're very small forces, so if you have small masses, you'll get to see those. And that's why we see millimeter grains, very sticky. Dust on the moon, very fine dust, sticks to everything. Sticks to everything because it's very jagged grains, lots of surface, and they van der Waals everywhere, basically.
Hi, thank you. Maybe smaller side, you were mentioning that there were like Jupiter-sized planets very close to other stars orbiting very quickly. Do you have any idea what the composition of those planets are?
Yes, so I'm not an expert in exoplanets, but they're Jupiter-style planets. They're made of gases, so a lot of the gases that you would find in, the universe, I guess, but also in our early system and in Jupiter itself. So you'd have hydrogen and helium, and then some of those gases, I'm not a specialist, but you can do, for those specifically, you can do good atmospheric analysis of what's all in there. And it resembles our Jupiter. So, it's a kind of a gas giant, but because it's so close, it thermally behaves somewhat different. It's inflated, it's redder, it kind of, the thermal, it's not as quiet, I don't know how to say, as the Jupiters that's out there. It's very thermally activated, I don't know how to say. So, giant, red giants, how we call those? Hot Jupiters. Yeah, thanks. The red giants are stars, sorry.
So, I'm just curious, is there any use looking at Saturn's rings and the shepherd moons and that rings to see how things...
So I didn't talk about it, but some of the stuff we work on is applicable to ring environments because it's a loose aggregation of grains that are also in basically no gravity with very gentle collisions going on. And yet, they haven't aggregated yet. So, but they're making these weird aggregates called granola bars. So some of the work we do is applicable to ring environments. But for example, the interactions with the gas that you saw, not really, but what I explained with the peloton, that would not apply to the Saturn's ring because there's no gas there, which could be one of the reasons why, because the aggregation of planets happens very fast on the time scales of, the universe. It's like we look at a system and 1 minute, I'm exaggerating obviously, but 1 minute it has a disk, the next minute the disk is gone. So, and when you do these simulations with the gas, with the peloton, you see that you just need a couple tens of years to make these, and then the dust is gone, you no longer see a disk. And so that the fact that there's no gas there could explain why it's not immediately aggregating into larger bodies. But Saturn's rings environments are very relevant also to what we do. Yeah.
Any other questions? Please, Have you ever tried to model planetary formation based on the behavior of cat hair?
On the behavior of what?
Cat hair.
What's that?
Your cat sheds,
Oh, cat hair.
and then it screws together like one.
Oh, yeah. Well, it's kind of, so the thing with cat hair, yeah. Yeah, so, cat hair, I think it easily loses and exchanges electrons. But you're laughing about this, but there's some crazy studies out there. There's some studies, for example, what if you put a magnetic field? And so all the aggregates you make are like elongated along the lines of the magnetic field. And so some people study, and obviously there's some charging. When you have a lot of friction with those grains, you charge them. So the charge question is always something I get. So we try to get rid of electrical effects so we really see the van der Waals forces. But there's a lot probably of tribal charging because these grains have friction and they will charge. And so how does that influence? It probably helps the aggregation. Although it won't help if you're too big. So you still have your golf ball problem. So you think you had a fun question, but it's actually relevant.
Why do planetoids not form accretion disks or hot holes?
So I didn't hear the whole question. What?
Why do planetoids not form in accretion disks of black holes?
Well, so black holes are a problem. But we've seen planets about way more exotic bodies than just stars. For example, when stars die, the smaller ones, they make neutron stars. And I think they found planets around neutron stars. So it looks like every time you have some sort of debris disk, you could end up with a, planetary system. But the problem with the black hole is if you're in the vicinity, the gravity here and the force you're experiencing here and the force you're experiencing there are so different that you would never be able to accumulate a planet because it's such strong gradient of gravity when you're close to there. And it's not my specialty, but it would be very difficult just because of that. But if you had a debris disk far enough, you could probably get planets there. There's debris disks around black holes, which is how we kind of see them because we cannot see them.
Does dark energy have anything to do with planet formation?
I hope not. At this point, I don't think so. So dark energy, right? A big mystery. We look out there and, the matter that we see behaves in a way as if there's some mass somewhere, right? The mass is not distributed as it should be. But we cannot see this mass. Mass equals energy, right? We cannot see it. So what is it? I don't know. Maybe it's a bunch of asteroids. You don't know. I'm just kidding. Don't quote me on that. So no, I don't think so. The physics we use here are not very exotic. They're very simple, electrostatics, gravitational physics. Nothing too exotic.
Thank you. Yeah, really quick, the videos that you have, will they be available anywhere on YouTube? I'd be interested in seeing what you were trying to present.
That's a good point.
If not, that's okay.
I'm trying to think. It's certainly a good point. We're working on our website, so I will bring that up at our next website meeting. I mean, some of those, for example, the very first video is in supplementary material and the publication that's associated with it. And then some in presentations we gave at some point, but the more recent stuff, probably not yet. But it's a good point. I'll think about it, yeah. To just excite the world about dust, you know. What?
Any more questions? Yeah, maybe not for one.
Oh, weird. Okay.
Great. If not, let's thank Dr. Brissett again.